Hello, everybody. As you might know, I'm working on a project related to autonomous vehicles, and for my project, I need to use LiDAR sensors to predict car accidents. And in this video, I will show you how I use this specific LiDAR, which is a 360-degree LiDAR sensor, to extract the data and manipulate the data so I can use it to predict car accidents. Now I am using NVIDIA Nano Jetson, which is a 2 GB single board computer. I am also using the ROS environment, which specifically is the ROS Noetic environment. And in my previous video, if you haven't seen it, you can watch it. I just show you how I set it up. In this video, I assume the setting up is not a problem anymore, so I will just show you how you can extract the data from the LiDAR and how you can manipulate it so you can use it for autonomous vehicles. Okay, so how do we extract the data from the LiDAR? I'm using ROSBag, so I don't need to use my hardware all the time. I'm just only using a simulation of my hardware, and this is just a replay. So pretty much I can run my hardware simulation. Then what I can do is I can simply say ROS topic list to see which topics are live. Seeing that this point cloud is active, I can check out ROS topic echo point cloud. And we get a bunch of data here. This is a lot of information. This is not really useful to us. Well, this part is useful, but I don't think this makes sense to anyone watching this video, unless if you like these nice curly shapes. But yeah, it is not really useful. And fun fact, this is all one list. It is one list containing all of this information, including all of this is contained in one list. You can see the list ends here and the new one starts here. So all the way from here, all the way it would have kept on going. Like it's a huge list. So we need to break this list down. How do we do that? Well, we need to create a subscriber. That's exactly what I've done here. We know the message, we know the topic is this. Now we need to figure out what kind of messages it uses. To do that, we say ROS topic info and point cloud. But we need to make sure this is running first. Point cloud. We see that it's using this kind of messages. So we're going to copy that. We're going to say ROS MSG show that. Now we see the message. This is what is inside the list. And fun fact, as I said, it's not just this. If it was just this, it would end like right over here. But there is a lot of this messages. Pretty much XYZ. It's like it's not just one point that it gives you like thousands of points in one list. So that's why it's so huge. And every time it makes a rotation, because it's a 360 LiDAR, every time it makes a single rotation, it takes maybe like 1,000 points. And all of those 1,000 points are in one list. So every rotation, you can think about it this way, every rotation of the LiDAR is one list, which means every list is going to be huge. Um, this took me a while to figure out, and I'll show you on an Excel spreadsheet how I figured it out because I had no idea why data was so huge. I didn't understand. Is this just maybe the same? Like there was so many possibilities of what this could have been, why this data was so big in one list. Now, using my subscriber, I was able to specify on this topic and this message, and I was able to put them into a function where I extract the data. So I have data extraction where I take it and I break it down into the points, the coordinates, and then the time. So this is done by, first of all, as I showed you here, first of all, breaking the points into X, Y, Z, and then the header into sequence, timestamp, and frame ID, which I'm not really sure. I don't think we really need that. So points and then X, Y, Z, which Z I don't really need because you might have realized that Z is always 0, which makes sense. It's a lidar. It only works on one plane. So the Z will be 0. And then timestamp is extracted from the header's stamp. It's like pretty big, but we get time in nanoseconds. Now, with this, we can print it out and we can see what we get. This will be much more usable information. This is much more helpful. Oops. So, if we run my Python 3 Lidar publisher or subscriber, and then we run the simulation, we can see the data like this. I'll pause it right now so we can read it. And you can see what it gives you is it gives you time, it gives you y, x, and time, yx, time, yx. This is all you need because we're trying to predict car accidents, we're trying to predict collisions. The only way we can predict collisions is if we look at x, y in terms of time. So if I pick a point, I want to see the same point after a second and compare it. Did it get closer to me? Did it get further away from me? And how fast did that happen? Now, that is why we need this information, time, x, and y. Now, another thing you might ask is, how do these points relate to each other? That is also another question I had. I didn't know if, so I have like x, I have y, and then I have x and y again later. Is that for the same point after some time, or is it the point that is like right after this point, adjacent to this pretty much? Is like it goes in chronological order, and then when does it get back? When does it meet? So when does it make a full circle? These are all questions that I had. The answer to this question I will show you in an Excel spreadsheet right now. Welcome. So right now I will show you everything on the Excel side. And pretty much what I've done is I have taken one of those lists which has a bunch of information. I've put it into Excel and you can see how huge this is. So this is all one list. It contains 640 points of X. This is only X. Then there is Y and Z. Z is always 0, which means there is a total of 1,280 values. That's a lot of values. Now, I was only able to understand what this means once I put it into Excel sheet because I was able to graph. And this might not mean much to you, but it made a lot of sense to me when I saw it. This is my room. Yes, you are right. This is my room. That is me in the center. This is my room. The lidar was placed somewhere around here. That's why there's more points around here. My monitor was somewhere here. So it only makes sense once you look at it this way. And this means, this is what proved that one rotation of the lidar is one list in the code. So one list in the code is indeed 640 points. It makes 640 points to go in one circle, and it places that in one list. This is another view. You can see that uh, by these lines, you can see that the lidar must have been somewhere here because it's like a perspective thing. I'm not sure if you guys have went through art class, but in art class, when you draw something in perspective, it looks like this. It's like from your origin, it looks like it's going out this way. So this is how you know the Lidar was placed somewhere around here. And I was here, that's why I was blocking the major part of this area because, well, you get it, I was there. So that's one question answered. What is this? Now, another question that I had is pretty much the way I got this data was by doing coordinates, and I didn't put anything in the brackets. So I just let the list print all of the list. And the way it printed, as you might remember, it was like info and then it was XYZ and a bunch of XYZs. And then after that it would just repeat, repeat, repeat. Now, because I want to determine, I don't need full 360 degrees. I only need a certain range because on cars, um, you activate different sensors, you do different things depending from where the collision is happening. If it's a rear end collision, you do different things. If it's a front end collision, you do different steps. So pretty much I need to know for my project specifically, I only care about the front side of the vehicle, which means I only care about less than 180 degrees, probably like 120 degrees. um, that means I need to specify the range somehow. So how would I do that? Now, one thing I've realized is if you say coordinates, which is the list, which is um, this one list is 360 degrees. So I can't use one list. Now I have to break it down further. What can I do? If I say 0, I put an index pretty much. I'm indexing it to only 0. I got something like this. And this is pretty much every round it made, it showed me only this one point. This is some certain point. I'm not sure what angle this is at. There is this might be where it might be a prefixed index, it might be angle 0, it might be anything. So pretty much when here, let me just move on to the next sheet. It will make more sense. When I specify coordinate 0, what is happening is it is pointing only at one single point. So this, all of these, this is 19 values. This is not from the same list. All of this is individual lists. How do I know that? Because every time the program says info, it's like resetting pretty much. It's being recalled. Every time it says info, it's a new list after that. So this is a new list, this is a new list, so is this, this, this. The information here is only from a single list. The information here is from many, many different lists. So this is from 19 lists. And that means this information here is coming from 19 different rotations of the LiDAR. From 19 different rotations, all of the points pointed to the same position. This proves the point that if you do coordinates and index it to 0, it will point here. Now, if I do indexing it to 1, it might be somewhere here, and then if I do index coordinates 200, it might be somewhere over here. You know what I mean? So this is really, really useful because now if I take coordinates and I say 15 to 20, I'm giving it a range. So I can give it an angle. And this way I can specify if I only need 180 degrees, I might want to say if there is 640 points in total, which we know from here, if there is 640 points, that means if I do 320 points, if I say 0 to 102, so if I do 0 to 320, what I will get is 180 degrees. I haven't tested this. This is what I think it will be. Now, if I get 120 degrees, then I can use that information to predict a car accident with pretty much saving a lot of space, a lot of RAM, a lot of CPU power. Now, another thing you might ask is, well, what is this graph here? This graph is pretty much showing you the accuracy. There is 19 points here. All of these 19 points are presenting the same point, but they are obviously offsite a little bit, and this is pretty much the accuracy of the point. As the lidar spin, every time it got certain deviation, it got a certain, like, this value and this value are very far apart from each other, but they're still trying to show the same point. So as you can see, it's in like the hundredth of a meter. So that's pretty good. Actually, I think this is a really good accuracy. Um, when you look at it from this side, it's pretty accurate. So now I will go back to the code and I will show you some other information that you should know. Looking back at the code, here is what we can do. Where before we would just take all the data for all 360 degrees, now we know that we can specify the angle by doing something like this, doing something like this over here with the range. We can specify that we want only 300 to 320, for example, which in my assumption will be exactly 180 degrees because 360 degrees was 640 points. So I am guessing that half of it would be this. The only difference is, the only thing that I'm not sure of is what angle is this? Because how, like, is this the right side? Is this the left side? Is this the front side? Is this the rear? Is this some weird angle? Maybe because we don't know yet. This is all trial and error. Maybe this range is facing the rear side. So who knows? Maybe I need to do um, negative 320 to 0. These are all very possible problems that we need to figure out, right? Maybe it's like 100 to negative 220 to 100. So we need to figure out the range. Now, this will be done in a future video where I will pretty much use the information from this video. Um, from the subscriber, I can extract all the data. And then what we need to do is create vectors. So take the point, a specific point, so maybe point um, 3, let's say, and then compare this point 3 with point 3 in the future, so at some other time, and by comparing them, you need to compare both x and y. So that means you compare the x from the x before and the y from the y before, which means you are pretty much finding a vector at this point. You have from the origin to a point, and then you have from the origin to another point, and then you find the difference in the two vectors, and the difference in the two vectors is gonna be the magnitude, and the direction is what's gonna tell you if this is moving towards you or away from you, and whether it's coming really quickly or really slow. Is this an emergency? Is this not? This data is really crucial for autonomous vehicles, and you will see this in the next video.